Nitrogen nucleophiles. Nitrogen is very different from oxygen, okay? So nitrogen is next door to oxygen, but it reacts in a very, very different way. Under acidic conditions, aldehydes and ketones will react with a primary amine. We're going to start with a primary, a nitrogen with 2 hydrogens and 1 carbon group, hence the primary, 1 carbon group, and it forms a new functional group called an imine. This was the reaction that actually occurs in our optical activity, right? When or in our eyes, when we're talking about seeing color and seeing the visible spectrum of the electromagnetic spectrum. This was one of the formations that occurs in the back of our eyeballs. So imines is a carbon-nitrogen double bond. That is a new functional group that you probably have not heard before, and we certainly haven't done the reaction before. It is under acidic conditions, but one thing I just want to say is that this is mildly acidic. We'll talk about the pH, but it's usually a pH around 5, not something so drastic like H2SO4. And so what we actually see is that this reaction mirrors better to our basic conditions. Okay, so we will start with a nucleophilic attack. And that is because nitrogen is more electropositive. It doesn't like its electrons. It can hold a positive charge much better than oxygen. And so the first step that we see is nitrogen attacking the carbon of the carbonyl and kicking up a lone pair. And then our mild acid conditions will be present for our proton transfer. Why we need those acid conditions is primarily because nitrogen is in at least a primary amine is not a good acid, right? The pKa of an amine is 35 to 38, and that is way too high. Think about oxygen. The pKa of oxygen, of a proton with an oxygen for an alcohol is around 16. So big old difference here between nitrogen and oxygens. So it might look like we're under acidic conditions, but it's mildly acidic. So we look more basic to us than other ones. Okay, so oxygen gets a proton to make it an OH, and then the conjugate base A will come back and deprotonate that nitrogen so that we're more neutral. This is a carbonyl amine. It's a carbon with an alcohol and an amine, and we'll keep going, all right? Oxygen will pick up a proton from the acid catalyst, and then nitrogen will kick out water. Again, water is going to be removed from the situation. Water is easily evaporated. There's a trap there that we can use most likely in the laboratory setup. And then acid catalyzed. So we'll remake HA plus by deprotonating the imine. And there it is. Even though it's under acidic conditions, protonation of the carbonyl is not the first step. And primarily it's because the ammonium ion is not acidic enough to protonate the aldehyde or the ketone, but it is acidic enough to do a transfer of a proton to a negatively charged oxygen in the second step. So we will have, again, mild acid conditions. You drop a little HCl in there, and what you actually have as your acid is an ammonium ion with a pKa of 10.5. Aldehydes and ketones have a pKa somewhere around 9 to 10. So we're not, or a protonated aldehyde or ketone. So we're not going to do the protonation of the aldehyde or ketone oxygen in this. It's not acidic enough. Again, pH has to be right around 5 or the reaction is too slow. Lower pH and all the amines are protonated, so none of them are able to actually be a nucleophile. At a higher pH, there's not enough acid to catalyze the reaction, and so we have to be right around the sweet spot here, which is mild acid in our terminology, which means it's somewhere in between an acid and a base catalyzed reaction. Under acidic conditions, aldehydes and ketones can react with a secondary amine as well. They cannot form an imine. They have to form an N-amine. An N-amine is an alkene with an amine right next to it. So we took an alkene and that ene ending plus an amine, and we merged it together in this lovely name, N-amine. The reaction requires acidic conditions to work, but again, the mechanism is identical to the imine formation, except for the very last step. How do we get that carbon-carbon double bond? So let's walk through this one. Again, nitrogen is strong enough to attack the carbon of the carbonyl, and then we will proton transfer to make the oxygen neutral. We'll deprotonate that secondary amine so that it is also neutral, and we'll get our carbonylamine. Proton transfer just like before of the oxygen. Kick out water. Now we're at a very, very important part. This is where we change, right? We had the loss of the leaving group, and now we have to do a proton transfer. Previously, to make the imine, we deprotonated the nitrogen. We don't have any more protons on our nitrogen because now we're using a secondary amine. So we have two carbon groups and we can't deprotonate that. So how do we make that nitrogen neutral? Is by giving its electrons back. And so we actually will deprotonate the adjacent carbon to make a carbon-carbon double bond and kick the lone pairs back to nitrogen. 1, 2, right? 1 and 2. So very different last step, and that is because of the type of amine we are using. If we use a primary amine, we have 2 hydrogens, so we can end up with the imine. If we have a secondary amine, we only have 1 proton, so therefore we have to end up with the N-amine. Either way, the Wolff-Kishner reduction is a 2-step synthesis that is actually extremely helpful. Nitrogen's nucleophiles don't just have to be amines. They can be different forms of the amine, right? So that R group that we were talking about before, right, doesn't have to be just a carbon, right? We'll do the reaction, lots of steps. And what actually occurs is we can make very, very different looking imines or N-amines. But with the imine, if we have this nitrogen-nitrogen single bond, we can use basic follow-up, KOH and water with a little bit of heat, and it actually will reduce the overall carbon to be an alkane. Very, very helpful in terms of synthesis. Not necessary for knowing the mechanism, not necessary for anything except for synthesis help. Again, just to remind ourselves, we can have the hydrolysis of acetals. The mechanism is the exact same, just backwards, right? So we can take an acetal just like hydrate and reverse the reaction, and we'll go back to our ketones or aldehydes. Acetals only react with water under acidic conditions though, so don't even try to use basic conditions to reverse on that one. And also hydrolysis of imines and N-amines are also reversible. They undergo very similar reactions to be reversible back to the ketones or aldehydes. Again, for practicing the reverse, the hydrolysis of these, add H3O+ and go backwards from the formation reactions.